generalization of the first law of thermodynamics that was obtained in classical thermodynamics. It was restricted to closed systems, systems with fixed mass, uniform, homogeneous systems. That means temperature and density remains the same. On top of it, the heat and work models that were used allowed for only reversible processes. So later on it was realized that the first law is not restricted to any of these conditions and can be generalized. And probably the final form of generalization takes the following form, in that I replace the time derivative in the traditional classical first law by the substantial derivative, so that it now applies to the energy and work done or heat transferred with respect to a body. It is here a collection of material points of fixed mass. And then the internal energy. On top of the internal energy, we need to add the kinetic energy of the body. And then retain the other terms where QR is the rate at which heat is added to the system and WR is the rate at which work is done by the system. Now we need to give specific, somewhat general forms for this. Based on the continuum approximation, I can represent the total internal energy of the body as an integral of the specific internal energy. Given like this, where epsilon is the specific internal energy per unit mass, locally defined at every point in the fluid. A similarly would be half rho v squared dV. V squared is V dotted V. QR, you are allowed for two forms of heat transfer. QR can be written as 2 of x V n, rather minus that refers to heat out. Typically, the heat flux is defined in that way, and plus integral O R D E. R represents the rate at which heat is added to the system through radiation, and it represents heat rate density per unit mass. So we have decided to neglect this, and the W we deal only with the mechanical part of the work done, not looking at other forms of work done. So in mechanics we have looked at two forces, right? Those two forces will contribute to the work done. The work done on the body, which is given by minus WR, can be written as the integral of the force times the velocity divided by the force density dotted with the velocity. So I will get E dotted with V dA plus rho V dotted with V dV. So this form is sort of easy. There are many terms. You can easily look at it term by term. You can infer how they are represented in a general manner. Right? So from this, our objective is to get a local equation energy balance. Right? So the local balance would mean that it is convenient to convert all the area integrals, which is here this and this. Those area integrals have to be converted to volume integrals, and then it leads to the local energy balance, which may be written as follows. That's not the one that we will use. So the local energy balance would take the following form. That is how the local energy balance will be. Now, a more widely used form of the energy balance rests on the mechanical energy balance, which is really an expression for dk by dt. And we showed that dk by dt is actually given by integral E dot with V dA. Plus, this is again easy to remember, because as I said, there are two terms, the forces, and we've already seen how the work done on the body due to those two forces are given. We derived this actually. And then minus another term, which is effectively will turn out to be the dissipation term. And given that this would typically turn out to be positive, right, you would find that that term, which has a negative sign of a positive quantity, would contribute to a decrease in the kinetic energy that represents a decrease in kinetic energy due to viscous dissipation. That means some form of mechanical energy is being dissipated, right, in the body. Right? So we now put these two together, we finally get a more convenient to use form of the local form. We will concern with the local form, and this would then this and this combined can be shown to lead to the following simple form of the local energy balance. This is still, so there are three basic quantities: the internal energy, the heat flux due to conduction, and the stress tensor. We need specific models for these, right, in order to be able to proceed further. Right? So we saw it took as a special, because now we have to specify what kind of fluid we are dealing with. We want to use this equation further. It's a very general equation. It doesn't say anything about whether it corresponds to a Newtonian fluid or a linear heat conductor or whatever, right, or an incompressible fluid. Then to further specialize this, to be able to apply it to specific problems, we need the specific fluids that we are dealing with. So we took the example, for instance, if I say a linear heat conductor is given by 2V. The 3 are not what I will consider. The fact that it's a linear heat conductor has nothing to do with the fact that it's going to be a linearly viscous fluid or incompressible fluid. So these 2 or 3 specific properties I'm going to list down are quite not interconnected. So if we assume that we have a linear heat conductor, that is, the fluid acts as a linear heat conductor, then we can apply the Fourier's model. It's actually not quite a law, but rather a particular model for a special type of class of fluids, right? Just as the Newton-Stokes relation between the stress and the deformation tensor defines a particular class of fluid. It's not a general law, like, for instance, the equation of motion or the energy balance. So this we have, and then we'll assume an incompressible linearly viscous fluid, for which then the rho is constant, and also the continuity equation is given by this. We know all the properties of the linearly viscous incompressible fluid, and further the stress tensor is given by. So with that we can first get this, and so we simply become minus a Laplacian of the temperature. This T is a temperature, not to be confused with the stress tensor. Right? So that term is taken care of quite easily. So we are assuming a fluid with a constant thermal conductivity. Then I can take the K out of the divergence of the heat flux. And then, so this is taken care of. Then we showed that for a symmetric stress tensor, generally possible to show that this is equal to this. And finally, with this, I can show that this quantity, when is the scalar coordinate of 2 tensor, that we defined actually in the last class. Defined like that. So that's a scalar product you have to understand. So scalar product of 2 tensors. For a linearly viscous fluid and incompressible, it's possible to show that this is simply equal to 2 minus 4 times the second invariant of the equation tens to all this. Now the question is, for particular problems, we'll see, we'll expand this quantity. Either you can write this as, evaluate this quantity as like this, or you can evaluate it like this with 2 entirely equal values for the incompressible fluid. Because the dii square, that term will become 0, because the trace of the deformation tensor is simply the divergence of the velocity vector phi, and that is 0 for an incompressible fluid. So you have to understand that some of these relations, this is a very general relation. This is valid when T is symmetric. Right? But the rest of the thing applies only to the incompressible linearly viscous fluids. You have to understand which is for a special case and which is general. Right? So once we have taken care of these 3 terms, and to further simplify the internal energy term in terms of quantities which are accessible experimentally and which are available in tables, and then we have to consider, we have to fall back on thermodynamics. Thermodynamics, the local internal energy, this is applicable only for equilibrium, what is usually used for thermodynamics. But however, here we are assuming a local equilibrium, that is locally I can assume in general, right? This is a famous relation from equilibrium thermodynamics, only for homogeneous systems. But here we can apply them to be valid locally. That's one of the reasons why in my course in thermodynamics I always define these fundamental equations in terms of the specific quantities, because they can be directly taken over to non-equilibrium or non-homogeneous systems with the local equilibrium approximation. That is, we assume that relations that are held true or regarded as true for homogeneous equilibrium states are valid locally for the specific quantities, right, in the case of non-homogeneous states. However, the important thing to remember is that even with an incompressible fluid, V or rho or whatever is fixed, so there will be no question of variation of the density. But also, as we have seen, the pressure is not a thermodynamic quantity for incompressible fluids, it's a mechanical variable. So the relation here for incompressible fluid has to be modified like this, and here, even though typically in thermodynamics it's used, this epsilon refers to per mole, and the S to per mole entropy, I will now here use it for per mass, right? So this is in internal energy per unit mass is related only to the entropy, and the specialization of the fundamental equation for incompressible fluid means that the temperature, which is a well-defined quantity here, is given by dE by dS. Right? So this is clearly T of S. Right? So this is T. And so I can invert this and write this as S equal to S of T, let us say. That's certainly allowed. Right? If it is allowed, then I can write E as equal to E of T. And then, because here the variable of interest is the temperature, right, and not the entropy. We want to get rid of that, right? So I can now define a specific E, dE by dT. I will define it as Cp. This is how the internal energy for a normal fluid is not incompressible. We define Cp as dE by dt constant volume, but here even the density is constant. So we leave it as it is and call it as Cp as it is done traditionally. Right? Because the other variable, the volume, has fallen out. I mean, it's not a variable with respect to the internal energy. It's not a variable at all. It is fixed for the incompressible fluid. So this is like, complication that arises out of the consideration of the incompressible fluid. And that is very, I can't see how a Cp can be defined in this case, because Cp relates to either we want to define it to the entropy, then it is T ds by dt at constant pressure, or it is dH by dt at constant pressure. Now here pressure is not a thermodynamic variable. Cp is cannot be defined for incompressible fluid. This is the point that is missed in most of the standard textbooks, and they all write the expressions in terms of Cp and so on. As far as I am concerned, this is the only way we have to stop here. You can equate it to Cp from, for instance, I mean, the problem arises because the incompressible fluid is a sort of a fictitious fluid. It doesn't exist, even liquid water. It is compressible to an extent, but it is, for all practical purposes, may be regarded as incompressible. From a thermodynamic point of view, we treat liquids as being compressible, but of a very low compressibility. So Cp is defined. What you find in tables for water might be Cp, right? But, and you can approximately take it to be Cv. For liquids, that's a reasonably good approximation under certain conditions. So you have to distinguish the practical aspects. The theoretical aspect, theoretically it is not possible to define a Cv for incompressible fluid. So you have to understand that. With that limitation, I can now write dE by dE. So dE by dE is this. This is the function of temperature, right? So now how I am going to regard the internal energy is that the internal energy is a function of temperature, but actually here as it appears, it's the substantial derivative, which is a partial derivative with respect to time, as well as a gradient, which is a spatial derivative. That means here E is actually regarded as a function of the position, right? And the actually as in terms of material coordinates, if I am going to use the substantial derivative. However, I am going to expand this as d by dt because d dot is with del for the gradient. So in which case, so that's a practically useful expansion. Right? I don't want to leave it as a substantial derivative. It's compactly written in this way. So that's what I want. Now, this is the local thermodynamic relation. So I'm going to write this as T as a function of T. This is going to give E of xt. Right, so you have to understand the transformation properly. To understand that properly, then dE by dt. So that means I am applying it here with x expressed as, or rather, I can write this as dE and dt by dt, which can be then written as Cv dE by dt. So T there is a temperature. So now I can further expand this once and for all as rather Cv, rho Cv. The rho is there, and there's going to be a Cv that comes from here. Finally, I want everything in terms of spatial derivatives, right? Because that's what is going to be practically useful. Whereas is equal to, I can, for the linear heat collector, I can write this as K times the Laplacian of the temperature, and then I can write this as minus this may be regarded as the final specialized expression, because finally we want an equation for the temperature field. That's what we have to solve in addition to the velocity field, because the density is constant for an incompressible fluid. So I have all these equations, the continuity equation, then what about the equation I have for the momentum that we have already written for the Navier-Stokes equation for a fluid with constant viscosity, linearly viscous fluid. And on top of it, I have to deal with this equation. So it's coupled really, because in what way is it coupled? If you look at the equation of motion, right? If you look at the equation of motion for an incompressible fluid, coupling here to the temperature. The coupling, if at all, will come to this, but T is, let's say, specialized to this. Now the incompressible fluid anyway pressure is a mechanical variable, so there is no coupling there also. The coupling, if at all, will come if the viscosity dependence on the temperature has to be taken into account. The fluid cannot be regarded as one of constant viscosity because it may depend on temperature. It is important if the temperature range in the fluid is high, right? Then we may have to take that dependence into account. Typically, incompressible fluid, even if it is not involving very high heating rates, temperature, we might, for all practical purposes, suppress the temperature dependence on viscosity, which means really for an incompressible fluid, the momentum balance is completely decoupled from the energy equation, right? Because after all, what is the final? If you take constant viscosity, then the viscosity can be taken out of this, and we got the answer, right? It would be this is what we get. So finally, there is no coupling because there is no temperature quantity, no quantity involving the temperature there. If of course the mu were dependent on the temperature, then I can't even write this properly. We will get some additional terms because which involve the derivative of temperature with respect to the spatial variations. Because I have the divergence here, which is basically a spatial derivative, and that is going to act on the viscosity if it depends on temperature. And since temperature depends on space and time, so we get some additional terms. If we neglect that, then the equation of motion is completely decoupled from the energy balance. So we get the velocity profile and the pressure profile by solving the continuity equation, and the equation of motion has been done all along. And then all I have to do is to substitute the velocity profile into this, and I can solve for the temperature. Single equation alone. Finally, I have to solve, and I'll get the temperature profile. So that's the simplification. That what it means is that I will take a simple approach, and whatever problems we have solved, right, for which we have already got the velocity profile, and simply going to use it and see what effect it has on the temperature profile in systems where there is heating as well taking place, right? So that is what I am going to do. The first example that I am going to consider, one example that is there in the assignment sheet from virtual life, but I am going to consider a few other examples, and the simplest example is the flow down a circular tube. Again, we are considering the incompressible linear fluid. So, flow down a circular tube, but with heating considered. So, this is the z-axis, right? So, constant A, and then one dimensional flow is what we consider in the z direction. And here we assume that the fluid is heated across the cylinder by a constant heat flux is provided. You see how to handle that. And then the fluid comes here. The fluid is coming here, and the temperature of the fluid is equal to this is z equal to 0, and we assume that the fluid temperature as it enters is uniform and given by T equal to T1. That is like the inlet condition. So the fluid comes with a uniform temperature at T1 from outside, and it's now going to flow through the cylinder, whereas heating is provided across the surface of the cylinder by means of some method which effectively provides a constant heat flux. So what I want to find is the temperature profile, right, as a function of Z as well as R. Right? So at any given Z, what is the temperature profile and how it evolves as the fluid flows down the tube. And let's say I'm providing positive heat, and then the temperature is going to increase, but it's going to have a profile with respect to both R and RC rather than Z. Okay? So I want to find the temperature profile. So the important thing to recognize is I'm assuming the viscosity is constant. The velocity profile is what I have already obtained, which is this I can use. Where is this going? So this is we assume steady conditions have been reached. So we want to reach a steady temperature distribution. So I make this to be 0. So the equation now is rho Cv T dotted with T is delta, which is going to be a function of Rc as well as Z. They are not making any approximation there. Other than that, the T is independent of phi. Equal to K minus 4 so I have to first calculate. So given the velocity profile, so once the velocity profile is given, then the deformation tensor is determined. And so the first quantity that I would have now to calculate is this. Because the rest of the things will just come into the equation. So I can further simplify this. If you look at this, now Vz is the only, so this can be written as Vz plus Vrc plus V phi. Right? So what I have is only this dotted with that the gradient of the temperature. So that we have two components, both the gradient component as well as the Z component, because however since this is dotted with only Ez, so the only component that will come out is the one involving the gradient in the Z direction. That alone will come. Right? So that would be Vz. So this term effectively would be rho Cv Vz dt by dz. Because of the fact of the velocity has a component only in the Z direction, even the gradient of the temperature has two components, only that component in the Z direction would come into play, right, on the left hand side. Now if I were to write this, I would have to have the Laplacian in the cylindrical coordinates. The Laplacian in the cylindrical coordinates would be k times 1 over Rc d by drc Rc dt by drc plus d square t by dz square. That's what we would get. Interestingly, birds with should neglect this. Probably worked out the example in birds with they actually neglect the d square t by dz square in comparison with this here. It is an approximation. So you can ask why it is not that dt by t is dependent on z is neglected. It has to come here. Otherwise, you lose the essential, information about the problem. But I guess it's an approximation. This is neglected in comparison to this, right? So we for a long tube in comparison to the radius, that might be a good approximation. So it is neglected here, but anyway, I have written it there. And then I have the viscous dissipation term. So what we do first is calculate the viscous dissipation term and see what it actually looks like. Now, if you look at the three invariants for any 3 by 3 matrix. The three invariants. And one is a trace you all know. The determinant also you know how to calculate. Right? So the second invariant for any matrix I am writing can be easily written because you have the diagonal terms. So I have to first write the terms. It's quite easy to remember. So I have the diagonal terms. This will have only product of two terms as opposed to the trace will have just one term. Product of one term alone in each term. The determinant for each term there will be 6 terms and each one would have 3 terms, a product of 3 terms. The second invariant will all the terms will be a product of 2 terms. And it's quite easy to construct. So what I do is first take the diagonal terms 2 at a time and then write it down. Plus, this is an easy way to write down the second invariant to any 3 by 3 matrix. Then everything else is subtracted. Now I look at the off diagonal terms, they will all come together, right? So I get A12 times A21. It's very easy to write out the characteristic equation for a 3 by 3 matrix. You can easily verify that the coefficient of lambda, I guess it's the coefficient of lambda square, so lambda, right? The coefficient of lambda will have this is the eigenvalue problem. So this would be negative sign on all the terms. All the off-diagonal terms, there are 3 sets of off-diagonal terms. A12 corresponds to A21. Only get the product of those two. Plus A23, A32. Everything is subtracted from this. So this is easy to write. Now in this particular case, right, if I were to write 5D, I can make use of the fact that D is a, this is actually I am writing in Cartesian, but it can be generalized to cylindrical as we will see. So, because 1, 2 and 3 correspond to Cartesian directions. Now, because D is symmetric, D12 is equal to D21 and D13 is equal to D31, D23 is equal to D32. So I can write this as D11, D22 plus D11, D33 plus D22, D33 minus, I can write it as D12 square plus D13 square plus D23 square. The symmetric matrix I can write it like that. So now how do we evaluate it? It's possible to show, because of the orthonormality nature of the cylindrical coordinate system, possible to show that effectively in the cylindrical coordinates, as I can simply associate 1 with RC as we have done, 2 with phi and 3 with Z, I can write down the second invariant by inspection in cylindrical polar coordinate or any orthonormal system. We can do the same thing for spherical polar also. So I get this is arbitrary. For convenience, I have chosen it like this, the way we have done it earlier. And so I can write this. I won't give a proof of this, but you have to take it as given. I can write this as DRC, RC, right? D phi plus DRC, RC, DZ plus D phi minus DRC phi square plus DRC Z square plus D phi Z square. Now, however, most of the terms will vanish here. If you look at this, dz dependent on RC. So the only terms that would come into play are the off-diagonal terms involving dz and RC. Right? So dz, RC and drcz are the only terms that are going to appear. All the other terms will be 0. Right? For this particular case, this is a general expression for cylindrical coordinates. Right? But in this particular case, the only quantity that would come out is drc z is equal to dzrc, because the symmetric matrix, and it will turn out to be half dz by drc. That's the only non-zero term. So if you look at this, this will be 0, this will be 0. So I pick this. So phi d would simply be minus drcz squared, right? And so I get plus 4 times mu times that. So minus dr is equal to minus 1 by 4 minus 4. I'm sorry, this is the minus 4. That sign is very important. You have to be very careful about that. So minus 1 over 4 dz by drc squared, and then I have minus 4 times viscosity times that. So the that term is going to be simply that is what the viscous dissipation term would be. So it's the square effectively proportional to the square of the velocity gradient. So this clearly you can see it is positive. Right? So it's going to contribute in a quantity. This is basically coming from the double dot product of T versus the gradient of the velocity. Right? So that is that term. It's a viscous dissipation term. Right? It comes with a negative sign. So then the T double dotted with gradient is what this is. That is going to be positive, right? Always. So I get this. So this is the additive term. So let's write now all the terms together and get the final equation, which is going to be somewhat difficult to solve, mainly because of the this term. Because it is multiplying, it will turn out to be a linear equation, OCB. So this is written as in terms of Vz max. This is not right out here. Times dV by dz is equal to A times. So I write only one of the terms. 1 over RC, then neglecting the other as an approximation. We get this, and plus this can be easily evaluated. Actually, I have to evaluate that. So since Vz is Vz max times 1 minus RC by R squared, clearly dVz by drc is minus Vz max by R squared times 2RC. Right, so the square of this, but take the square of this, so that would be 4 RC squared, that's the square, by R power 4, that's square that Vz max squared. So when we rewrite it, it's 4 this is where the dependence comes in. So this is also going to complicate the solution of the equation. Both of these terms, right? Because it's a function of RC that multiplies that derivative. So it's not such a, because it's a linear equation, it is going to be difficult to solve analytically directly. It can be solved probably by some kind of an eigenfunction expansion. So let's now look at the boundary conditions. order in RC. So I have to specify the two boundary conditions in the R direction and one in the Z direction. One in the Z direction I've already written, right? So that would be a Z equal to 0. So I can write E of 0 RC is simply equal to a constant D1. It can be also have a profile. Here we are assuming a uniform temperature profile at the inlet to the tube. Right? Now the two boundary conditions on the typically it is there's an R equal to 0 because the boundary for RC equal to 0 and RC equal to R and RC equal to 0 you have to impose the condition that the E is finite. Probably it is equivalent to dB by dRC being equal to 0. We see that later, right? So let me just write it down. And at RC equal to R, I have the heat being transferred to the constant heat flux through conduction. So I can write this as here I will first write. So Q naught. I have to explain because Q is often written minus K dB by dRC. What is Q naught? I mean, it's coming in and out, all that we have to take into account. So this is broadly we have run out of time, so that's why we take this up in detail in the next class. Work out in virtual language. So what he does is actually non-dimensionalize the equation. So he introduces the following non-dimensionalizing quantities. And then the temperature non-dimensionalized as follows: T minus T1 by Q naught R by K. R is the radius of the cylinder, capital R. And then you have a non-dimensionalized variable in the Z direction that is given by Z. You see the rational verb when you put CB equals CB Z max R squared by K. So when you do this, you get a strikingly simpler equation. We will derive this in the next class and we'll see how to solve it. Well, 16 times some number called the Brinkman number times psi square, where the Brinkman number is given by, I'll let you try to derive this in terms of the non-dimensionalized variable. Given these definitions, boundary conditions would also simplify, and we will simply get psi equal to 0 is finite. Just finish with this. Psi equal to 1 equal to 1, and at theta equal to 0, the dimension temperature is simply equal to 0 due to definition. Let's slightly simpler equations to deal with because we've got rid of the parameters in this equation by proper non-dimensionalization. So we'll take up the solution and what the profiles would look like in the next class.